this lesson, we're going to look at nomenclature, so how we name compounds. We'll explore chemical formulas, and we'll talk about the difference between naming ionic and covalent compounds, and also defining what ionic and covalent compounds are. We're first going to start with chemical formulas. Chemical formulas are often referred to as compounds. So what is a chemical formula? It's a combination of symbols that give not only the type of element that is in there, but also the number of atoms of that element in a compound. And that is represented with subscripts. So here are some examples below. So first example, we have NaCl. So just looking at this chemical formula, I know that Na, sodium is present in it. That's what the Na stands for. Notice it's an uppercase N and a lowercase a. Okay, that tells me both of those letters belong together and are referring to one specific element. The element it's attached to is Cl, or chlorine. So I have sodium and chlorine together. Now the subscripts tell me how many atoms of each of those elements are present. Now notice there are no subscripts in this particular formula. So when there are no subscripts, we assume there's just one, meaning there is one sodium atom present and it is combining with one chlorine atom. Because remember, compounds always come together in whole number ratios. So that's why we know it's one whole one. We're never going to see halves. All right, looking at the next one, CH4. Notice they're both capital, capital C, capital H. So that tells me those are two different elements. The first one, C, when I find it on the periodic table, I see that it's carbon. Since there's no subscript after it, I know there's just one of them. Now for hydrogen, or the H, which is hydrogen, there is a subscript after it. So that tells me there are 4 hydrogen atoms in this compound. So the ratio of carbon to hydrogen is 1 to 4. Last but not least, this compound has carbon, hydrogen, and oxygen in it. And each one of those elements has a subscript. So carbon looks like has 5 carbon atoms in this compound, 12 hydrogen atoms, and 2 oxygen atoms. So that's how we read the subscript. The subscript that comes after the chemical symbol indicates how many atoms of that particular element are present in the compound. So subscripts refer to the element preceding the subscript. And as we said before, if no subscripts are present, assume one atom of that element. So now that we know what chemical formulas look like and what they represent, let's define an ionic compound. So how can you tell, just by looking at a chemical formula, if a compound is ionic or if it's covalent? Well, for ionic compounds, you would just find both of those elements that form the compound on the periodic table, and if one of them is a metal and the other one's a non-metal, then it's ionic. So we have a nice little cheat sheet here. Notice the metals are in this hot pink color and the non-metals are in the yellow color. So remember, with ionic compounds, it's in the name, they're going to be comprised of ions. So when we talked about ions previously and predicting the charge of ions, remember metals like to lose an electron and form positively charged cations, and then nonmetals like to gain an electron and form negatively charged anions. So that's why they go so well together. The metal likes to give electrons away, the nonmetal likes to receive those electrons. Once they form their charges, the positive charge on the metal and the negative charge on the nonmetal are attracted to each other since opposites attract, and those electrostatic forces is what holds the compound together. An example here is CaCl2. So we have calcium. So if we find calcium on the periodic table, we can see that calcium is in pink here. So it's a metal, more specifically an alkaline earth metal. Then when we find chlorine on the periodic table, we see chlorine is a nonmetal. So this is definitely an ionic compound. We have a metal with a nonmetal. And notice the nonmetal is a halogen, salt former, right? So now that we know how to identify if a compound is an ionic compound, how are we going to name ionic compounds? So a series of questions you want to ask yourself because there are several different types of ionic compounds. So there's the standard naming system, which is the group A metals, so the alkali metals and the alkaline earth metals. So there's a specific way to name those. Then there's a slightly altered version when there's polyatomic ions involved, which we'll discuss later. And then when you get to the transition metals, so if a transition metal is present in the ionic compound, then there's an extra step. So we're going to go through all three variations of the ionic compounds, starting with the standard, which is generally the easiest with those alkali and alkaline earth metals. So you want to make sure to ask yourself, first off, when you're naming an ionic compound, confirm that it is indeed ionic, that there is a metal and a nonmetal, or a metal and a polyatomic. If it is ionic, then you ask yourself, are there polyatomics? Because then you're going to have to go to the second way of naming that we'll cover later. And last but not least, if there isn't, are there metals involved that are transition metals? Because remember, transition metals have multiple possible charges, so that's going to be a little bit different to name than the group A metals who have definite charges. So here are two examples of ionic compounds, and more specifically, their main group ionic compounds. And you can confirm that on your own. So the metal always comes first when we're looking at the chemical formula. So notice sodium is the metal, oxygen is the nonmetal portion in this first compound. The second compound, magnesium, is the metal, chlorine is the nonmetal portion. So the metal always comes first. Now, sodium is an alkali metal. If you find it on the periodic table, you'll see that it is number 11, and it is in that first group, being an alkali metal. And then magnesium is an alkaline earth metal. It's number 12 on the periodic table. And so they're both main group metals, and they have specific charges. We know that sodium, since it's an alkali metal, will always form a +1 charge. Magnesium, since it's an alkaline earth metal, will always form a +2 charge. Okay, so just looking at the chemical formula, we can already tell a lot of information. But let's move forward and look at naming. So how are we going to name these compounds? Well, you start by naming the first element, which we said is always going to be the metal in an ionic compound, or the more metallic of the two at least. So the first element, name it with no special ending. So for the first one, it would be sodium. No special ending, just straight off the periodic table. And remember, the metal portions are the cations. They're the ones that are losing electrons. And we already mentioned that sodium specifically is going to form a +1. Now for the second element, the nonmetal portion, we are going to alter that one a little bit. So we're going to name it, but add an IDE ending to it. And remember, the second element is the negative portion, the anion. That's what holds the ionic compound together, the cation and the anion, those opposite charges. So for this first example here, sodium and then oxygen is going to become oxide. So sodium oxide. For the second one, so we name the first element, the metal first, magnesium, no special endings, and then chlorine is going to become chloride. Let's do some more examples together. So here is the general layout of how we're naming. So the more metallic or the positive ion is going to be named first with no special endings. Then the nonmetal portion, the negative portion, we're going to use the root name and add an IDE ending to it. So NaCl, I'm sure we've named this a million times already, but let's try again. So Na is sodium, so we write just sodium, just how it is. And then chlorine is going to become chloride, so we add an IDE ending to that. Now for this next one, Li2O. Now notice there are 2 lithium atoms. That doesn't matter when we're naming how many atoms there are. We still name it the same. So Li is lithium, And then O is oxygen. So oxygen needs to have an IDE ending. So oxygen actually changes, to oxide. A lot of people want to write oxygenide. That's not correct. So it's just oxide. KBr. So finding K on the periodic table. Notice that's an alkali metal, just like lithium. So K is potassium. Br is a halogen. So it's bromine. So bromine would become bromide. Last but not least, CaCl2. Ca is an alkaline earth metal. It's calcium. So we write it just how it's written on the periodic table. And then Cl, chlorine, becomes chloride, as we saw in the first example. Not only do you need to be able to take a chemical formula and figure out what the name of that particular formula is, but you need to be able to go in the reverse. If you're given a name, come up with the formula. So how do we do that? With ionic compounds, what we're going to do is you need to know the charges. So your first step is to, of course, read the name. So in this case, we have magnesium bromide. So we would find magnesium on the periodic table and write down its symbol with its charge. So here's magnesium, number 12. It looks like it is an alkaline earth metal, so it has a +2 charge. And then bromine is the other component of this compound, the nonmetal portion. And bromine's a halogen, so it has a -1 charge. So we write down both symbols with the corresponding charges. Next, we need to make this compound neutral. So the ionic compounds that we have been naming so far have all been neutral, and this was neutral as well, or it would have the word ion after it if it had a charge. Okay, so right now, looking at them, if I had just one magnesium and one bromine, will the charges cancel out? No, they won't in this case, right? We have a +2 charge on magnesium and a -1 charge on bromine. That's not going to cancel out. We're going to be left with too many positives. So what we need to do is add another bromine. If we add another bromine atom, now we have a -2 charge on the anion side, and that'll cancel out the +2 charge on the cation side. So to figure out the formula, it means we need 1 magnesium and 2 bromines. So the formula becomes MgBr2. So steps: write out the symbols with the charges, and then figure out how many atoms of each you need in order to make the compound neutral. Now, there's always more than one way to do things, so here is another way to figure out the chemical formula based off of the name, and it's called the crisscross method. Now, the crisscross method is where you go through the same steps, so you're going to have to take the name and go to the periodic table, find the elements, and then what their charges would be. So aluminum in group 13 is going to form a +3 charge. So they wrote Al 3+. Oxygen in group 16 always forms a -2 charge for us in this course. So we have O 2-. Now how does the crisscross method work? The charge of one ion becomes the subscript on the other, meaning we crisscross them. So this 2 that's on oxygen is going to be the subscript on aluminum, meaning we need 2 aluminums. Notice we're going to take the number but not the charge, because we don't want -2 aluminums, right? So you just bring the number down. And then for oxygen, since there's a 3+ on aluminum, 3 is going to become the subscript on oxygen. So we get a formula of Al2O3. And you can even write it out to make sure that it is neutral, right? If we have 2 + 3, or 2 aluminums, that's going to be a total of +6 on the cation side. For the anion side, since we have 3 oxygens and each oxygen is worth -2, 3 times a -2 is -6. So we have a +6 on the cation side and a -6 on the anion side. So it is indeed neutral. The trick with using the crisscross method is that sometimes you will need to simplify it down. So I have an example shown here. So if the subscripts can be reduced to smaller whole numbers, do it. So with the case of calcium oxide, so if you look at calcium on the periodic table, it is an alkaline earth metal, so it has a 2+ charge. And then oxygen has a -2 charge. So if we were doing the crisscross method, it would look like we need 2 calciums and 2 oxygens, when indeed we don't, right? If we just had one of each, it would still be neutral. So that's why if you can simplify them down when you're doing the crisscross method, you need to in order to get the correct one. All right, so now we've learned how to name the main group metals when they're in ionic compounds. So next we're going to look at polyatomic ions. So polyatomic ions consist of 2 or more atoms that are bonded covalently. So if you look at this table of common polyatomic ions, you'll see that most of them are nonmetals with other nonmetals. And nonmetals bond covalently with other nonmetals, and we'll see that when we talk about covalent compounds next. But you'll also notice that they have a charge on them, right? They're ions, so they're either going to have a positive charge in the case of ammonium here, or they're going to have a negative charge, which is the case of most of the other ones. Since they have charges, we use them as either the cation portion of ionic compounds or the anion portion of ionic compounds. Now this is just a list of common polyatomic ions, and you do need to memorize the polyatomic ions for this course. So you have been given a list, and there's a list on Blackboard as well if you lost the list. So make sure that you are studying those and remembering those, because it's going to be important to name those not only for this test, but you're going to need to name them in future tests as well as the final. So let's jump right in and figure out how to name some of these. The nice thing about naming ionic compounds with polyatomics in it is you name them exactly how they're written in the polyatomic table. So you don't have to add any ID endings or anything like that. The metal portions, you just keep exactly how they're written on the periodic table as well. So not too difficult. So let's look at this first one that's listed here. So SrNO3. I want to point out as well, you'll notice there's parentheses and then the number 2 on the outside of the parentheses. Whenever you see parentheses in a chemical formula, that is telling you, hey, there's a polyatomic in there, okay? Because those parentheses are encompassing that polyatomic. So that's a nice hint that there's a polyatomic so that it can help you name it appropriately. So this number 2 on the outside is saying there are 2 NO3 groups. All right, so let's name it. So Sr, looking at Sr, it is an alkaline earth metal. It's number 38 on the periodic table. It is strontium. Now NO3, that's a polyatomic we've already established. And when you look it up on the polyatomic table, or once you memorize it, it's actually nitrate with an ATE ending. So strontium nitrate would be the name of that guy. Next one, we have Al2SO4 sub 3. Notice parentheses again, so that's a big red light saying, hey, there's a polyatomic here. Okay, so the metal portion we named just like before, so finding Al on the periodic table, we see that it's aluminum, so we would write aluminum for the metal portion. And then SO4, that would be the memorized polyatomic portion. SO4 is sulfate, also ATE ending. So aluminum sulfate is the name of that guy. Now in this next one, notice we have no metals in it. Okay, but it's still an ionic compound even though we don't have metals in it, because what we actually have is 2 polyatomics together. So notice this first portion, this NH4, that's a polyatomic. It's ammonium. It has a +1 charge, so it can be used like a metal since it is a cation. Okay, so NH4 is a polyatomic. It's ammonium. And then NO3, we've already seen in that first example, that's a polyatomic as well, and it's nitrate. So ammonium nitrate. And the reason there's no parentheses around this is because there's only one ammonium polyatomic and only one nitrate. So there's no parentheses needed unless there's more than one polyatomic in the chemical formula. All right, let's look at the next example. The metal portion is this K. That is the alkali metal, is potassium. The polyatomic is this Cr2O7. So the name of this guy is going to be potassium chromate. Now let's try to do some examples with the reverse. So here you will see names of different ionic compounds. Some of them have polyatomics in them, and some of them are just nonmetals for the anion portion. So in order to figure out what the formulas are for each of these compounds, we first need to start by writing the elements or the polyatomic and their corresponding charges. So I'll go ahead and pause it and try to do that on your own. Otherwise, I will talk through it and put them all up here. So potassium is an alkali metal in group 1, so that's going to have a +1 charge. Chloride is just chlorine with an IDE ending, and chlorine is a halogen, so that will have a -1 charge. The next example, we have strontium bromide. So strontium is an alkali earth metal with a +2 charge. And bromine is a halogen. It's bromine with just the IDE ending. So that's a -1 charge. Next one, potassium. Potassium is represented by the symbol K. It's an alkali metal, so it will have a +1 charge. Nitride, since it has that IDE ending, we know it's just a nonmetal on the periodic table, and it's actually nitrogen. So nitrogen becomes nitride, and nitrogen likes to form a -3 charge. Now for the last two, we have magnesium, alkaline earth metal with a +2. Now notice the nonmetal portion, or the anion portion. It's nitrate, so notice it has an ATE ending. So since it has an ATE ending instead of IDE, that tells us it's going to be a polyatomic. And in this case, it's NO3 with a -1 charge. Last example, aluminum. Al is the symbol, likes to form a +3 charge. And then notice we have a polyatomic again with that ATE ending. Sulfate, and sulfate is actually SO4 with a 2- charge. So here are all of the charges that we just discussed. So now you can either do the crisscross method or add atoms to either the anion or cation side until it balances out. So for this first one, you can see there's just one of each, so the formula would just be KCl. For strontium bromide, you would need 1 strontium and 2 bromines for it to be neutral. So SrBr2. It's kind of getting a little messy for me to write. Now potassium nitride then, so if you think about doing the crisscross method, you would need 3 potassiums, so it would be K3, and 1 nitrogen, so just K3N. Magnesium nitrate, looks like you would need 2 NO3s, so 2 of the nitrate polyatomic, and then just 1 magnesium. Now the trick for writing this one, since there's more than one of the NO3s, you want to make sure that you put parentheses around that polyatomic, because if you don't put parentheses around it, it's going to look like there's 32 oxygens. And we don't want 32 oxygens and 1 nitrogen. Instead, we want 2 nitrogens and 6 oxygens. So that's why we put the 2 on the outside of the parentheses. Now this last one, looks like we're going to need 3 of the sulfate polyatomic and 2 of the aluminums. Just take a minute to write that down. And since there's more than one of the polyatomics in this case as well, more specifically, there's 3 of them, make sure to do parentheses with the 3 on the outside. So we've covered the main group compound naming system and the polyatomic ion naming system. Let's look at the last and most difficult way, which is ionic compounds that contain transition metals. So transition metals, remember, they have variable charges. That's this whole section in blue. Remember, these are all the transition metals. So since they have variable charges, and we don't know what their charge is, we need to figure that out in order to name it. So for instance, iron is a transition metal. Sometimes it's +2, sometimes it's +3. For copper, sometimes +1, sometimes +2. Cobalt, similar to iron, sometimes +2, sometimes +3. So since it has variable charges, we need to somehow indicate that when we're naming ionic compounds that have transition metals present in them. So how do we do that? We indicate what the charge is on the ionic compound on the metal portion by writing Roman numerals in parentheses immediately after the metal's name. So with the case of iron, since we can have an iron 2+ or an iron 3+, we would indicate which charge it is by putting a Roman numeral after writing the word iron. So for iron 2+, we would do Roman numeral 2. For iron 3+, we would do a Roman numeral 3. So here we have a chemical formula, FeCl3. So we're going to figure out how to determine the charge when we're just given the formula itself. So looking at this, we just said we don't know the charge on iron, right? It could be a +2, it could be a +3. So looking at iron isn't going to help us. What would help us is to start with the ion that does not have a variable charge. So what I mean by that is let's look at good old chlorine here, because we know what the charge on chlorine can be. Looking at the periodic table, chlorine is a halogen, meaning it has a -1 charge. So we go ahead and we can write that down. So we write chlorine with a -1 charge. Now we do need to pay attention to how many chlorines there are, because remember, this compound overall is neutral. If it had a charge, the charge would be in this upper right-hand corner. It would be a superscript after the chlorine. So since there is no charge, we know it's neutral. And it has 3 chlorines. So I'm going to write all 3 chlorines. Each of those chlorine ions has a -1 charge. So that is going to give us a total of -3 on the anion side. So what do we need on the cation side to cancel out that -3 charge on the anion side? We're going to need a +3, right? +3 plus a -3 equals 0, neutral. So that means we need a +3 on the cation side. So looking at iron, it looks like there's only 1 iron atom present. Since there is no subscript after it, we assume it's just 1. So that means that entire +3 charge is going to go on that 1 iron atom. So that tells us that we have iron 3 in this particular compound. So to name this compound, we need to make sure to use Roman numerals in parentheses immediately after the metal ion's name to indicate the charge on that. So for this particular compound, since we know it's got a 3+ charge, we would write the metal name, iron, then Roman numeral 3 to indicate it's a +3 charge ion, and then the chlorine portion we name just like before. Chlorine becomes chloride, adding that IDE ending. So here are some examples, and I'm going to go through them and just tell you what the names of them are instead of trying to write them down with this finicky pen that I have here. So looking at the first example here, CuO. So notice Cu, if you look for it on the periodic table, it's copper, it's a transition metal. So that means we're going to have to write the name with a Roman numeral indicating the charge afterwards. And to figure out the charge, we need to look at what it's attached to. So in this particular case, it's attached to oxygen. And remember, oxygen has a -2 charge. Also notice in this chemical formula that there is no subscript after oxygen, meaning there is only one of them. So that means we have a total of -2 charge on the anion side. So for this compound to be neutral, that means we have to have a +2 charge on the cation side. And since there's only one copper, that means that entire +2 charge goes on copper. That's a 2, sorry if you can't see. So now that we figured out copper is a +2 charge, or it's copper 2 that we're using, we can now name it. So to name this one, you would write copper, parenthesis, Roman numeral 2, and then oxygen becomes oxide. All right, let's look at the second example. Very similar, but notice the only difference is now this subscript of 2 after copper, meaning there are 2 copper atoms in this compound. So to figure out the charge on copper, we do the same process. We know that oxygen has a -2 charge. There's only one oxygen in this case, so the total anion side is -2. That means our total on the cation side needs to be +2. However, since there are 2 copper atoms, that means each of the copper atoms are going to have a +1 charge. Because if each has a +1, that's going to be a total of +2 on the cation side. So in this second example, our copper that we're using is copper 1. So when we write the name of it, we would write copper, Roman numeral 1, and then oxygen becomes oxide. So copper 1 oxide. Let's look at this final example. Now for this final example, I'm going to use the reverse crisscross method. Because remember how we did the crisscross method before is we would take the charges and the charges would become the subscripts. Well, I'm going to do reverse where the subscripts become the charges. So this is a nice trick that sometimes works as well. So that means this 3 that's on the outside of that polyatomic, that's going to be the charge on iron. So it's going to be iron 3+. Now this 2 that is on iron, that's going to be the charge on the sulfate. And I want to double check in my polyatomic table and make sure that SO4 really does have a -2 charge. And it does. So that means this way is working for me. So that means we have an iron 3+. So since we know what type of iron it is now, we can name it. So iron 3+, how we name that is we write iron, Roman numeral 3, and then since it's a polyatomic, we just name the polyatomic. So SO4 is sulfate. So iron, Roman numeral 3, sulfate is the name of that guy. Now let's do the reverse with these other ones. So this first one, manganese 4. So the fact that it has a 4 after it tells me what the charge is. That means it's a +4. Because that's what the Roman numerals mean for transition metals. It means the charge of the ion. Oxide is really just oxygen. And oxygen has a -2 charge. So what you can do is the crisscross method. So the 2 becomes a subscript on magnesium, and then the 4 becomes a subscript on oxygen. Now this is a case where we're going to have to simplify it down, and you'll see what I mean here in a moment. So I just said manganese 2 and oxygen 4. Now we said whenever you're using this crisscross method that you might want to simplify it down if you can, and in this case we can, right? There's a 2 and a 4. We can simplify that down to a 1 and a 2. So the correct chemical formula, once we simplify it down, is going to be manganese, so Mn1O2. It's going to be the correct one. All right, let's try silver 1 nitride. So silver 1, that's telling us that it is silver with a +1 charge. So if you find silver on the periodic table, it is a transition metal. We can tell that because of the Roman numerals. Its symbol is Ag, and it's a +1, we said. Now nitride is really just nitrogen. We find nitrogen on the periodic table. We see that it is in group 15, so it likes to form a -3. Notice you should always have a positive cation with a negative anion. Okay, if you have two positives or two negatives, you did something wrong. All right, so doing the crisscross method on this one, it would tell us that we need 1 nitrogen and that we need 3 silvers. So the formula would then be Ag3N. That's a 3. All right. Next, let's do cobalt 2 perchlorate. So cobalt 2 perchlorate, you're going to write CO with a +2, find the perchlorate ion. Since it has an ATE ending, you know it's a polyatomic, so you find that polyatomic on the periodic table along with its charge, and then do the crisscross method for that one. Okay, I'm going to go through this last one quickly as well. We have ammonium sulfite. So ammonium is a polyatomic. You're not going to find it on the periodic table. It's actually NH4 with a plus. So it's no metal present in this one, just 2 polyatomic ions. You then would find sulfite on the periodic table, which is SO3, and its charge, and then do the crisscross method to figure out the chemical formula on that one. Sorry, it's getting hard to write. Next, let's look at covalent compounds. So what exactly is a covalent compound? Covalent compounds are when 2 or more nonmetals combine. So that means we're focusing on the yellow sections of the periodic table in this particular periodic table. And the thing about covalent compounds is they share electrons. Okay, so this is different than ionic. Remember, ionic compounds, the metal gives electrons away and then the nonmetal takes those electrons. So we have charged components that are attracted by opposite charges. With covalent compounds, there is no charges. They share. Okay, so no ions are formed. They're often referred to as molecules instead of just covalent compounds. So an example here is this N2O5. So looking at that formula, you could figure out that it is indeed a covalent compound because nitrogen is a nonmetal and oxygen is also a nonmetal. So that tells me, yes, it's a covalent compound. So how do you name covalent compounds? Well, covalent compounds, I enjoy naming them a little bit more than ionic. I don't feel like they're quite as complicated. So looking at this particular example, the first element present, you start by naming the element itself. So no endings, no changes, just straight from the periodic table. Very similar to ionic compounds, right? The metal portion came first and we would just write the metal name with no changes. The second element present, just like with ionic, we want to add an IDE ending to it. Okay, so this is all very similar to what we've seen so far. Now this table off to the right is going to be helpful. It's showing the most common nonmetals and what their IDE forms look like. So fluoride, chloride, bromide, iodide, those are pretty straightforward. The ones people usually get confused are hydrogen, right? Hydrogen becomes hydride, not hydrogenide. Oxygen becomes oxide. Phosphorus becomes phosphide. Nitrogen, nitride. And then sulfur, sulfide. Now the thing that is different with naming covalent compounds is this third and final step, prefixes. Okay, so since there are no charges with covalent compounds, prefixes are needed to indicate how many atoms of each type are present. So here are the prefixes that we'll use based off of the subscripts. Okay, so you look at the subscript that comes directly after the element symbol to figure out what the prefix should be. So goes from mono all the way to deca. We probably won't see more than deca in this course, but you have those off to the side to refer to. This is not given to you on the tests, so you will need to remember this, memorize it. 5 is penta, 6 is hexa. so on and so forth. So for this particular compound up here, its name would be dinitrogen due to the number 2 subscript after the nitrogen. And then oxygen becomes oxide, but we need a prefix. So the prefix in this case, since there's a 5 after the oxygen, is going to be pentoxide. Let's try another one. So CO2. So looking at this compound, you see that there is carbon, and there's only one of them. So that would be the first element name is carbon, so we write it straight off of the periodic table. The second element present is oxygen, so we want to add an ID ending to that. So oxygen will become oxide. Now for the third step, to add prefixes. So since there's only one carbon, and we know that because there's no subscript after the C, so we assume it's a 1, we would write mono before carbon. And then for oxygen, since there's a subscript of 2, we would write dioxygen. Now when you look at this, monocarbon dioxide. Have you ever heard of monocarbon dioxide before? My guess is no, but you probably have heard of carbon dioxide. So here comes our first rule. The prefix can be dropped on the first element if mono, but not on the second element. So this is an exception to the rule. So prefix is always dropped on the first element if there's only one of them. So it is indeed just carbon dioxide. Let's look at another example. So in this compound here, first off, we know that it's covalent because there are 2 metals bonded to each other. Chlorine is the first element present. Oxygen is the second element present. So for the chlorine, since there are 2 of them, we need to add the prefix of di. So it would be dichlorine. So no changes to the ending of this chlorine because it's the first element present. Now the second element, oxygen, we will change that ending to IDE, so oxide, and since there's 7 of them, we need to add the prefix of hepta. So we get dichlorine heptoxide. Now oftentimes when we have 2 vowels next to each other, in the case of heptaoxide, they drop the A on the hepta and just have heptoxide. But I do want to point out you are not graded on your spelling, so if you were to write heptaoxide, I would not count that incorrect. Just want you to know for when you see them in the future if you had questions on it. Let's try a few more practice problems in naming the covalent compounds. So at the top of the screen, we have the general outline for naming covalent compounds. So you want a prefix comes first and then the element name of the first element. Then another prefix in front of the second element name, and the second element name needs to have an IDE ending. The charts off to the right will help you get the correct endings as well as the correct prefixes. Remember though, you are not given those prefixes or the IDE endings on the test, so you will have to know how to do those. All right, let's look at this first example, pH 3. So looking at P on the periodic table, it is phosphorus and it is a nonmetal. So in this case, we would just write phosphorus. Why? Why would we not put a prefix? Because there's only one phosphorus. And remember that rule with carbon dioxide, that if there's only one of the first element present, we do not write mono. We just write the element's name. So phosphorus, and then there are 3 hydrogens, it looks like, attached to it. So that would be tri for the prefix, and then hydrogen becomes hydride. Next we have N2O3. So looking at this one, N is nitrogen, and there are two of them. Since there are two, our prefix would be di, so dinitrogen, and oxygen is attached to it, more specifically three of them, so it would be trioxide. Can't forget that IDE ending on the second one. Last example, SCl6. So once again, notice the first element present, there's only one of them, so we're not going to put a prefix on it. So in the case of S, that means it's sulfur. So we'd write sulfur, no prefixes, no alternate endings. And then for the chlorine that's attached to it, hexa for 6 of them. And then chlorine becomes chloride. So we get sulfur hexachloride. Now let's look at how we write formulas of covalent compounds. So if you're given the name, how do you change that into a formula? So first off, we use the element names themselves, go to the periodic table, and figure out what their symbols are, because that's how we represent chemical formulas, using the symbols and using subscripts. How do we know what the subscripts are going to be? Because of the prefix. That's the reason for the prefixes. It tells us how many of each. So if it says tetra, we know there's 4 of that particular element, so on and so forth. It indicates the number of atoms of that element. The number of atoms then becomes the subscript immediately after the element symbol. So remember, make sure that subscript is after the symbol that it's representing. So an example we have here is dinitrogen tetroxide. So the prefixes tell us how many of each, and then we use the names and find the corresponding symbols on the periodic table if we don't already know them. So for dinitrogen tetroxide, nitrogen is just a capital N on the periodic table. We would put a subscript of 2 after it due to this di prefix in front. For oxide, that's really just oxygen with an IDE ending. So the symbol is a capital O. And then the tetra tells us there are 4 oxygens. So now we can put it together and we get N2O4. Corresponding chemical formula for dinitrogen tetroxide. Here's a summary of the types of bonding that we went over. So starting with ionic, you can see there are several different types of ionic bonding, ionic compounds, ways to make ionic compounds. And this makes sense if you look at the periodic table, because remember, ionic compounds are generally metals with nonmetals or else with polyatomics. So since there's way more metals on the periodic table than there is nonmetals, you would expect there to be a wider variety of combinations. So here's all of the types. We have a metal with a nonmetal is one way. Then we can also see a metal with a polyatomic. So that's where you name the metal straight from the periodic table, and then the polyatomic name straight from the polyatomic table. We can also see a polyatomic with a nonmetal. So remember, if the polyatomic is the first thing present, it's going to be a positively charged polyatomic, because the cation always comes first in an ionic compound, and then the anion will come second. And last but not least, polyatomic with a polyatomic. So this would be where you have a positively charged polyatomic bonding with a negatively charged polyatomic to get those opposite charges in that ionic bond. Now looking at covalent bonding, most often we'll just see nonmetals with nonmetals, but you will see a few cases with a nonmetal and a metalloid. And a lot of times that will be with boron and some other ones in group 3 or 4. So here's a practice problem that you can try on your own. I'll go over the steps to trying to figure it out. So in this situation, we are studying ionic compounds by dissolving the compounds in water and determining how many ions are in each compound by using a conductivity meter. The higher the value on the meter means more ions are present. So we have a list of the compounds we're working with. Of course, they're all ionic compounds since we're talking about ions and charges. So we have lithium chloride, potassium nitrate, rubidium sulfate, and potassium phosphate. So the first question is asking, what are the chemical formulas of the compounds listed? So to figure out the chemical formulas, you need to find those elements on the periodic table or the polyatomics, because I can see right here a lot of ATEs. So potassium nitrate with the ATE tells me that that is a polyatomic. Rubidium sulfate with the ATE tells me that's a polyatomic. And then of course we have phosphate as well. So there are 3 polyatomics in here. So write down the metal and its charge. And they're all main group metals, so you can figure out the charge simply by looking at the periodic table. And then write the nonmetal or polyatomic portion with its charge as well, and then do the crisscross method to get the subscripts to see how many of each ion there is. Once you have the chemical formulas, you can answer the second question. Which compound would have the highest reading on the conductivity meter? So remember it said the higher value on the meter means the more ions present. So you'll count the subscripts, and whichever one has the highest number of ions in it will have the highest reading on the conductivity meter. So the last thing that we're going to learn how to name is inorganic acids. So acids produce hydrogen ions. So hydrogen ions being hydrogen atoms with a charge, a plus charge more specifically. So they produce H plus ions when they're introduced to water. That's the definition of acid, of an inorganic acid. Now we're first going to learn how to name monoatomic acids. So notice we see the word mono here. So mono meaning one. Okay, so monatomic acids with halogens. How do we name those? First, we shorten the hydrogen part to hydro, because monatomic acids with halogens are always going to start with hydrogen. There's always going to be a capital H in the chemical formula. So instead of writing the word hydrogen, we're going to shorten it to hydro because we know it's an acid. Then for the acid portion of the halogen, so say it's chlorine for instance, we're going to drop the INE of the gas and add ic. So instead of chlorine, we would write chloric. And then of course you need to add the word acid at the end. So let's look at some examples. This one I actually just did without realizing it. So HCl, since it's starting with a hydrogen, and once it's exposed to water, it's going to form an inorganic acid by forming H plus ion in water. So to name it, since it's monatomic, we are going to, instead of writing the word hydrogen, shorten it to hydro. And then the chlorine part will become chloric, and then the word acid after. So hydrochloric acid is the name of this guy here. Let's do another one. So here we have HBr, very similar. So instead of hydrogen, we write hydro. And then bromine becomes bromic. And then we write the word acid after. So HBr is hydrobromic acid. Next we have HI. So notice we're going right down the list of halogens. So hydro once again for the hydrogen. Iodine becomes iodic, and then we add acid at the end. So hydroiodic acid. So now we're going to look at naming polyatomic inorganic acids. So on the previous slide, it was monatomic. Here it's polyatomic, meaning we're using a polyatomic ion in it. So it's going to be hydrogen with a polyatomic ion. So there's 2 different rules depending upon what polyatomic you're talking about or what the ending of the polyatomic is. So if the polyatomic ends with a ATE, Then you replace the suffix, meaning you replace the ate with ic and add the word acid. Notice we're not writing hydro at all. We only write hydro for the halogen monatomic inorganic acids. Okay, so no hydro on the polyatomic ones. So HClO3. Well, since HClO3, we're looking at just the polyatomic portion to help us name it. So ClO3 is chlorate with an ATE ending. So since it has an ATE ending like we just saw, we want to change that ATE ending to ic instead. So this acid will be called chloric, and then of course don't forget the word acid after it. Now looking at the next example, we have hydrogen with NO3 polyatomic. And if you remember, NO3 polyatomic is nitrate with an ATE ending. So we want to replace that ATE ending with ic, so it's going to become nitric acid. I'm just going to put quotes here so I don't have to try to write it with this funky pen here. All right, now let's go to the second set of rules. So if the polyatomic ends in ATE, we replace it with ic. But if it ends in ITE, then we change it to us. Of course, don't forget the word acid. So since it's a polyatomic, we're not using the word hydro. So we're just looking at the polyatomic to name it. So here we have ClO2. So ClO2 is chlorite with an ITE ending. So since it has an ITE ending, we want to change that ITE ending to us. So it's going to become chlorous acid. Now the second one, we have NO2, which is nitrite with an ITE ending. So nitrite will become nitrous. So HNO3 is nitrous acid when we name it. Here's another example for you to work through on your own, and I'll give hints to help you get started. So strong inorganic acids are causing harm to forests and statues in the form of acid rain. You notice the cause may be from coal fuel source. You need to see the following names and compounds while researching: sulfuric acid, HNO3, H2SO3. So the first question is asking, what is the chemical formula of sulfuric acid? Okay, so to help you figure that out, first of all, you know that there's going to be a hydrogen in front. So H, and that the hydrogen is going to have a +1 charge, because that is the definition of these acids. They form H+ when dissolved in water. Now for the polyatomic side, and I say polyatomic, I know it's a polyatomic because there's no hydro in front of the name. If it had a hydro in front of the name, then it would be a monatomic acid. Since there's not, I know it's a polyatomic. So sulfuric, how do I know what polyatomic? Well, remember we add IC to the ending of any polyatomics that end in ATE. So that means we're looking at sulfate. So the sulfate compound, or sulfate polyatomic, you would need to find on the polyatomic table, or hopefully you have it memorized. And sulfate is just SO4 with a -2 charge. So go ahead and do the crisscross method to figure out what the subscript should be, and you have your chemical formula. Now number 2, what are the names of the two chemical compounds? So both of those chemical compounds, HNO3 and H2SO3, have polyatomics in them. So you would look up the polyatomic for NO3, which we saw in the previous slide was nitrite, find the appropriate ending, and name it, including the word acid at the end. Since it's a polyatomic, hydro is not needed. Same goes for H2SO3. Find the polyatomic SO3, whatever ending it has, change it appropriately, and add the word acid at the end. Number 3, a little bit of a confusing question. It kind of answers itself in the question. What type of compounds are these acids in water? They're acids. I mean, it kind of already said that. So, sort of a silly question. So here are the answers from the previous question. For sulfuric acid, it shows you what the formula should look like after you do the crisscross method. And then also the names of the other two formulas, so nitric acid and sulfurous acid. And then of course, when acids are dissolved in water, they form acids, but also ionic compounds because they separate into their ions. So H+, and then whatever they're attached to, the anion, would also be in solution. And that's the end of this section.